Hi, my name is Michaela Bartram, and this is Lab 7. Today, our main objective is to find the mass of a black hole through data regarding a star in orbit around it. We have the star's mass and its position, and we'll use those things to find its momentum and then find the mass of the black hole it's in orbit around. The main physics principles that we will be working with initially are momentum and curving motion. The first equation, we see the momentum principle. If I divide the change in momentum by time, I get change in momentum over change in time equals F net, which is very important. Below that, we see F net equals change in momentum over change of time, which I just proved above, is equal to the sum of the parallel and perpendicular momentums. The formulas for parallel and perpendicular momentums are shown, and that's what I used for my code. The next thing I did was update my starter code with the new data from WebAssign. Right here, I updated the mass of the star to 1.989 e to the 30. I didn't have to update my delta t because 60 times 60 times 24 is 86,400, which is the number of seconds in a day. And then if you scroll down, we can see what I did in lab last week. I had to find initial velocity, final velocity, initial momentum, final momentum, as shown. And I went down and I had to find my dt parallel, which is change in momentum over change in time in the parallel direction, which is also equal to the F net parallel. I did the same thing for perpendicular. I found F net perpendicular, and then I found F net, which is equal to F net parallel plus F net perpendicular. You see my arrows. I have one arrow for perpendicular force. I have one for parallel force. dp dt is equal to F net. And I have one for F net overall. And I will show you what happens when I run my code. Now I'm going to run my code, run module, and we see my yellow star rotating. My blue arrow is my F net parallel because it's parallel to the initial momentum. It's pointing backwards from the direction that the star is moving because the star is decelerating. So instead of being parallel, it's anti-parallel. So it's just parallel pointing in the opposite direction. My red arrow is F net, which is pointing to the center, which is somewhere around here. And you can see my black arrow, which is perpendicular to my initial momentum, which is in the direction of the parallel one. So you can see that the perpendicular is perpendicular to the parallel, and F net is pointing in the direction of the net force in the middle. When I ran my code, I was a little bit concerned that my star did not travel in a complete circle, so I went ahead and plotted the sample data of the position and graphed it in Excel, and as you can see, I only have the data for about less than a half of the orbit. So my data is correct, and my model follows my data to the T. I manipulated the gravity formula for force of gravity from one object onto another. I took away all of the r hat because I don't need a vector in the end, I need a mass. I took away the negative from the g because that's only relevant when position is relevant and we're not looking for position. And I manipulated the formula to find m2 and plugged it into my code. I plugged my formula into VPython here. G is a constant, and I set that equal to 6.7 e to the negative 11, and I put everything in for my formula. I had to find r, position of the star, minus the position of the black hole, which was given to me in WebAssign. I had it print black hole mass, and I got 1.981 e to the 31. I put that into WebAssign, and it was correct. What does this mean? I had my arrows already showed you for F net parallel, F net perpendicular, and F net overall. And these quantities relate to delta p over delta t parallel, and delta p over delta t perpendicular because they are the same numerical quantities. The difference is where they come from. Delta p over delta t comes from the change in position over the change in time, whereas F net comes from the forces acting on the object. It isn't just a numerical calculation, it is the forces themselves. What if the mass of the black hole was different because it was replaced by a different black hole in the exact same location and the star moved in the exact same path? I could not tell the difference. This is because we calculated the mass from the change in location between the two, which would still be the same because they're both going to still be in the same location. The force of gravity would be the same because our F net would be the same because our momentum over change in time would be the same. G is a constant, so it would be the same, and the mass of the star would be the same. Therefore, the mass of the different black hole would be exactly the same, and we couldn't tell the difference between the two.